it loses energy. So this energy is released as a light photon. So what is the energy? What is the wavelength? Okay, cool. Where's my paint program? Come on, paint. Come on. Waiting for it to open. Oh, there we go. It's loading. Loading. Loaded the brush. And the window menu. There we go. Right. A1. So the energy 3 to 2, it will be minus 2.416 minus 5.424 times 10 to the minus 19, but that's equal to HF, which is equal to HC over lambda. So therefore, the lambda will equal HC over E, which will equal HC over minus 2.416 plus 5.424 times 10 to the positive 19, if I bring them to the top. So I bash this into my calculator, and what do I get as my wavelength, if you have it there? 660.8. So 661 nano. Okay. 2. Determine the energy of the photon emitted in electron volts when it moves from 4 to 2. Ah, the same thing again, except they just want the energy. So the energy when it goes from 4 to 2 will be minus 1.360 minus 5.424 times 10 to the minus 19, and they want that in electron volts, so divide that by E, and how many electron volts we get? 2.51. Explain why transitions to the E1 level will result in spectral lines in the UV region of the electromagnetic spectrum. So they want to know why when the energy moves, when the electron jumps to E1, it will release a UV. They want to know why is that. Well, just think about it like this. Here is E1, and here is En, we'll say. Okay, so which one's, this one's bigger, this one's smaller. So if I do En minus E, that's the energy of the photon. But we know that's equal to HF. So that is HC over lambda equals En minus E. So lambda equals HC over En minus E. Now, they want to know what UV, I suppose what I want to do now is calculate the two possible extremes. Like the wavelength should be in between two values. And I think the point that they're making is those two values that's in between is always going to make it a UV. So what's the biggest this could be? The biggest this could be is when this is the smallest. And what's the smallest this could be? And remember the E1, I should perhaps be a little bit clearer. That E1 doesn't change because they tell us that it jumps to E1. It's only the En that could be a different value. So if I want to make this bigger, I need to make this smaller. If I want to make this smaller, I need to make these closer. If I want to make these closer, then it means I should use the E2. because that's the closest it can be to E1. And then on the other end, if I want to make this smaller, I need to make this bigger. To make this bigger, I need to make this difference bigger. To make this difference bigger, I would use the En that's furthest away. No, that's just the one that they tell us, but there's E5, there's E6, and so on. But what's happening as you increase the energy levels? Yeah, and I should say actually what's happening to the energy as you increase the levels? It's getting closer to what? 0. So the most I could have here is 0 minus E1. Okay, so let's calculate the two extremes. You probably have this one calculated. What wavelength did you get? 122 nanometers. Now, maybe you don't have this one, so it's HC over 21.73. .4 nanometers. That's kind of, UV is like at 150 or something like this. 150 or Yeah. So what's the broadest range you could have for UV? Lee, you have your phone handy there. Type in a wavelength range for UV. I'm just curious to how close we were. Anyways, it doesn't really matter if you don't know this because you can just pretend you do.
100 nanometers to 400.
100 to 400?
100 to 400.
But if it's 100 to 400, then that means this is not UV. What did you get? Actually, hang on. Hang on, I'll get it. UV wavelength. UV is from 100 to 400. From 100 to 400. So actually, yeah, you kind of have to round off a little bit here because this obviously is within 100 to 400, but when it's really small, like 91.4, it kind of falls outside the range of UV. So this is UV, mostly. Now I've only 2 marks, so I think I've done way more than what they would actually need. In fact, I don't even think in the marking scheme that they'll do this limits. I think they'll just imagine the extreme case, which is perhaps what you did, E4 to E1. Not 90. Oh, yeah. Oh, yeah. They instead of using 0, they used E4. Yeah. You see, what I don't like about that is in the question it doesn't say the 4 energy levels. It says the lowest 4. Guys, wait. I just want wait. Before your question, I want to draw your attention to something. Please note in the second sentence it said the lowest 4. It didn't say the 4. It said the lowest 4. By saying the lowest 4, that's meaning that there are more than 4. In the marking scheme, they used E4 as if E4 was the biggest energy. But of course it's not, because there's more energies after this. The biggest one would be near 0. Okay, what's your question?
Isn't it a nanometer? Means something times 10 to -6?
No, that's micro.
No.
9 is nano. Okay. Anything else, Monica, with this? No? Okay.
Yeah, even though there's a times of negative 9, I got 6.6 times to negative 7 meters.
Yeah,
Sorry.
6.6?
6.7.
6.7? Yeah, okay.
And then if it's times to negative 9, it has to go
6.7 times
Yeah,
10 to the minus 7 is 67 times 10 to the minus 8, which is 670 times 10 to the minus 9.
I didn't like. Oh. Yeah.
Wakey, wakey.
Sorry.
Okay.
I thought it did.
Close this one? Yeah. The next one looks like it's different now. We're on to half-life.
So teacher, what is
Oh, the answer is the wavelength will always be between these two, which is UV. It's not really UV, it's just nearly UV. But we won't draw your attention to that. Okay, I can close this page. Lee?